Hello, this is Elizabeth A. Albright. Welcome to Probability Video 3, a short video on discrete probability distributions and more specifically looking at the binomial distribution. And yes, that is me on the bike pedal in clay. Thank you for joining today. So the roadmap for today's video is we will start with discussing random variables and then move on to discrete distributions. We will finish with the discussion in an example of binomial distribution, a type of discrete distribution. A random variable x, and that's a large X or a capital X, is a variable whose outcomes are generated by a random process. A random process such as flipping a coin with potential outcomes of heads and tails, or whether someone voted or didn't vote. So the probability of capital X equals X. This is the notation that represents the probability that the random variable X equals some value X. For example, probability large X equals heads equals 0.5 for a fair coin. Random variables can either be discrete or continuous. In this video, we will look at discrete random variables. The number of values that a random variable x can assume is finite or countable in a discrete probability distribution. For example, discrete probability distribution of the number of Category 3 or stronger hurricanes making landfall in North Carolina in the upcoming season could be predicted based on modeling to resemble the table presented here, where you have x and the probability that x equals x. So 0 outcome, 0 hurricanes of Category 3 or stronger having a probability of 0.6. 1 probability of 0.2, 2 probability of 0.18, and greater than 2 probability is 0.02. Again, these are approximations. One could model the upcoming hurricane season, or right now the current hurricane season, and make predictions on number of expected landfalls to occur in the state of North Carolina. The binomial distribution is a discrete probability distribution under a certain case. This is when we have a set of binary independent events, often called trials, with two outcomes, such as success and failure, yes or no, presence or absence, correct or incorrect, true or false, voted or didn't vote. And each trial must be independent. The result of one trial must not affect the probability of outcome of another trial. And the probability of success, or P, must remain constant across all trials. So let's think about combinations first. If you flip a coin 4 times, again, this is a binary outcome, head or tail, what's the probability of getting at least 2 heads? We will assume that this is a fair coin with probability of heads being 0.5. It's a slow flip. Let's speed it up. Flip, tails, heads, heads, tails. Oops, sorry, tails. And we could think about all of the possible combinations, right? And so head, 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 tail, head, 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 tail, head, 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 tail, head, and I could go on. I will not drone on there. The number of possible combinations of 4 flips, each flip having the option or outcome of head or tail, we have 2 to the 4th, or 16 potential outcomes, 2 being heads or tails, 4 being from the 4 flips. In this case, it's 4 trials. So what's the solution? Each combination, each of those 16 is equally likely if we have a fair coin, 50-50 coin. That probability is 0.5 times 0.5 times 0.5 times 0.5, or 0.5 to the 4th, or 1/16. And 11 of the 16 combinations satisfy the criteria of at least 2 heads, right? We could count those up and count those that meet the criteria, at least 2 heads. So 11 out of 16 is a probability of getting at least 2 heads in a series of 4 independent coin flips, assuming that the probability is constant across those flips. The probability of heads of 0.5, tails 0.5. Right, so we could do this for whatever problem we are facing, but it would get taxing, right? That's a lot of combinations to write out. So we have the binomial. So I'm going to work through the binomial formula to solve this same problem, just so we understand the mechanics behind it. So binomial distribution is fixed number of observations or trials, and the outcome is either success or failure. It's binary or dichotomous. Probability of success is P, and is constant across all observations. So the probability of K successes in N trials is N choose K, P to the K, 1 minus P to the N minus K. And the mean of this distribution, the mu, population mean, equals N times pi, or the pi is the population probability, or P. The variance, or sigma squared, is N times pi times 1 minus pi. And that pi, just to be aware, is not 3.14, right? It's the probability. So let's take that first chunk of the equation, or the formula first, and dig into that. N choose K. I write it this way. There's a couple different ways you can write it. And that equals N factorial over K factorial, N minus K factorial. If you're not fresh up on your factorials, I recommend Googling factorial or going to the Stats Review site to check out factorial. So in the case of the coin flip, or the 4 coin flips, N equals 4 flips. And we want to know the probability of when K equals 2, 3, and 4, right, or 4. In other words, at least 2 heads. So let's look at the case of 2 first. K equals 2. So you have 4 factorial, 2 factorial, 4 minus 2 factorial equals 24 divided by 4, which equals 6. 6 ways to get 2 heads. This is the same thing we found when we wrote out all of the possible combinations. Let's do it again for 3. K equals 3. We have 4 factorial over 3 factorial times 4 minus 3 factorial. This is 24 divided by 6 equals 4, and so there are 4 ways to get 3 heads. Then we have K equals 4, 4 factorial over 4 factorial times 4 minus 4 factorial. We know that 0 factorial is 1. 4 factorial divided by 4 factorial is 1. So there is one way to get 4 heads. That's intuitive there. And so how many ways are there to get 2 or more heads on 4 flips? We would add these up. Same as we found before. There are 11 ways to get 2 or more heads. Same as when we wrote out all of the 16 combinations. So that's that first part of the distribution formula. Let's do the second part now. Here is the formula again. Probability K successes and N trials. N choose K, P to the K, 1 minus P to the N minus K. Remember that P is 0.5. K is going to be either 2, 3, or 4, and N is 4. So let's look at the 2 K's first. Probability K equals 2. That 6 is from the last slide. 6 ways to get 2 heads. And then that's 0.5 raised to the 2 times 0.5 raised to the 2. And that gives us 0.375 probability. As you can say, we could have written that in shorthand, 0.5 raised to the 4. Probability K equals 3. There's 4 different ways to get 3 heads. And we multiply that by 0.5 raised to the 3. 0.5 raised to the 1, and we get 0.25. And one more time, k equals 4. This equals 1 times 0.5 raised to the 4 times 0.5 raised to the 0, and that gives us 0.0625. So what do we need to do? Sum across those three probabilities to get the probability that k is equal to or greater than 2, and we get 0.6875. And if our math works out, that should be the same as 11/16. So again, we just worked through the intuition of the binomial distribution. So now it's your turn to practice a problem. Here's a binomial example. You have a plot of 20 blooming statisticus. It's an endangered plant species in the Piedmont of North Carolina. Plants of this species have a 60% chance of flowering in May. What is the probability of 10 of the 20 plants flowering in May? Please also state the assumptions we need to make for the binomial distribution to hold. Please stop the video and complete the problem, but please don't forget to come back. Thank you for coming back. Let's now go over the solution. The problem gave us n equals 20, the number of plants. And we're interested in finding the probability that 10 of the 20 plants bloom. So k equals 10, or 10 successes out of 20, with a constant probability of 0.6. So we have 20 choose 10, 0.6 raised to the 10, multiplied by 0.4 raised to the 20 minus 10, or 10, and we get a probability of about 0.12, or 12% probability. We could also put this in R with the function d binom with the arguments x, comma n, comma p, or 10, comma 20, comma 0.6, and we get the same solution, 0.117. Finally, we need to think about the assumptions underlying the binomial distribution. First, we need to think about the independence assumption, that the trials are independent, meaning that the propensity of one plant to bloom does not influence the probability of another plant blooming. Right? So we need to think about and know a bit about the biology of the plants and study them to see if there is kind of spatial patterning in blooming across the 20 plants. The second assumption we should think about is the constant probability of blooming. Do all 20 plants across the plot have the same probability of 0.6, same chance of blooming? Right? And if these assumptions do not hold, then we may need to think about another way to model the blooming of these plants in the plot. Right? We need independence and constant probability to use the binomial distribution.